Greeting everyone, I'm Sebastian Deneroșca, based at the University of Petroșani, and I'm happy to present our paper titled CCVAP-based BCI control of robot swarm. The three main chapters describe are the introduction to terrestrial and aerial environments, the BCI system used in robotics, our prototype, how it works, and our conclusion so far. Robotic research has always aimed to simplify, optimize, and replace repetitive and time-consuming tasks. Manually or automatically controlled robotic systems often do not meet the expected requirements, either due to high complexity or poor adaptability in complex environments, or the fact that they do not cover the needs of all people, especially those with disabilities. For those reasons, the development of biologically inspired robots that can act like a swarm has become a trend. Such robots capable of communicating with each other and those with collective computational intelligence are often found in military and civilian applications, such as natural disaster management, rescuing potential victims of forest fires, earthquakes, and floods. Inspired robots from natural behavior of insects and vertebrates, swarm robots can be coordinated in the execution of tasks that the individual could not perform in all areas, like aquatic, aerial, but less in terrestrial. The best example is the collective movement of ant colony that makes a bridge shown in this figure to transport prey into the colony using pheromone routes to find shortest paths. This natural behavior was mimicked by the puzzle bot swarm robots presented in this figure, developed by a researcher from the Institute of Robotics, Carnegie Mellon University, USA. Each module was developed as a low-cost alternative being manufactured by 3D printing and can be interconnected by a passive coupling mechanism to be able to support the weight of 389 modules. They determine the trajectories of each robot using the 4 motion trackers based on Beacon motion tracking system. An example of self-organized behavior with potentially partially decentralized model are the formation of Gs during migration as presented in this figure. In this type of model, there is no single central leader. The strongest flyers take the lead in the absence of hierarchical structure, but what is remarkable is the fact that each individual bird knows what their neighbors are doing based on local observation and communication. The natural decentralized model was transposed through a swarm of drones, experiment developed by the researcher from the Department of School of Aerospace, Transport and Manufacturing from Cranfield University, United Kingdom. They involve 2 DJI Tello Edu drones, present in this figure, to carry a coordinated light load based on the leader and follower relationship. The leader drone was programmed to fly autonomously through relative waypoints, and the follower drone based on the estimation of the leader position following a green cotton marker. Next, BCI system used in robotics. Even if swarm robots can operate on a large scale autonomously, the presence of the human operator is mandatory in many situations where decision and skill are needed. Correction to improve autonomy, bypass restricted areas, or switch to manual control are potential operations that the operators need to transmit to the distributed system leader. A direct communication path from the supervisor intent to the leader of the robotic swarm can be established through brain-computer interface. This type of interface measures the brain activity through electroencephalogram sensors placed on the user's scalp to produce mental patterns that can be translated into commands. Each of these commands can be used as inputs for a computer or for the robot itself. BCI systems are classified according to how the electroencephalogram signals are obtained as endogenous, based on motor imagery produced in the motor cortex, and exogenous, known as visual evoked potentials, produced in the visual cortex. The steady-state visual evoked potentials is used in the field of neuroengineering as an indicator of person intentions or volition. The potential of CCVAP is used in BCI due to the most of their spectral energy is concentrated in a narrow band. The attention is what voluntarily modulates this energy. The visual stimulus can be, for example, an elaborate shape similar to a chessboard in a circular position that is animated to reverse its pattern to act as stimulus as presented in this figure. Next, our solution propose a brain-computer interface that we developed in the Unity 3D game engine to control a decentralized quadruped spider robot swarm formed by two identical 3D printed robots. Each robot presented in this figure was the result of 3D modeling in Autodesk 3D design to fit with 12 high-torque servo motors that provided 3 degrees of freedom for each leg. In next figure is presented the hardware block diagram of quadruped swarm. We choose to use as hardware solution an Arduino Nano V3 board together with an expansion board and a Raspberry Pi W0 to ensure the communication through Wi-Fi based on user datagram protocol. As a BCI solution, we use NextMind BCI headset to acquire EEG signals of the user because it provides nine patented dry active electrodes placed in accordance with the International 1020 EEG system adapted to measure the brain activity from the visual cortex. In next figure is presented the interface of calibration manager provided by NextMind SDK that we implemented in our solution to measure the user attention level obtained as response of the visual stimuli to be used as reference for active control. Here is presented the frame of the graphical interface developed in SolidWorks computer-aided design software in the form of a honeycomb with 6 round holes. Each of these coincide with the movements implemented for each robot that is pseudo leader. We relay messages to the follow robot. These include forward, reverse, turn left, turn right, sit, and stand. Next, we implemented the result of CAD modeling into Unity 3D, and we created 6 3D objects in a sphere form, augmented with neurotag provided by NextMind to be used as a visual stimuli input for the CCVAP BCI system. Each neurotag are programmed to flicker at the monitor user frequency rate to induce a stimuli response in the visual cortex and based on machine learning algorithms. The NextMind headset are able to decode brain activity to recognize the active visual focus of the user. We implemented triangle feedback prefab in every sphere to identify what sphere are chosen by the user focus. As conclusions, in our experiment, we used the user intention of visual cortex level detected through CCVAP BCI system as non-muscular inputs to control in tandem a 3D printed quadruped spider robotic swarm based on 6 movements replication predefined by us. The main advantage of our solution based on visual stimuli is that it doesn't require prior training over complex mental commands as motor imagery. In our implementation, every robot can act itself as a pseudo leader because it's a part of this centralized model behaviors through communication implemented by UDP protocol. And in this manner, this solution can be expanded to control up to 253 swarm robots using a single gateway. Next, I want to present a short movie with our solution functionality to control these 2 spider robots based on the visual stimuli. As can see here is the calibration menu. And next, uh, the six movements: forward, backward, left, right, sit and stand. Thank you for your attention.